Good afternoon, everyone. My name is Joanne Lefebvre, in case you don't know that. I'm the chair of the Department of Cognitive Science, and I'd like to welcome you here today for our keynote speaker. Before I introduce our speaker, though, I would just like to acknowledge the Algonquin Nation, whose traditional and unceded territory we are gathered on today. Our speaker, as you all know, is Dr. Andrew Brook. And Andy is very familiar to some of us, including myself, and not very familiar to some of you. So I'm going to tell you a little bit about him and provide you with some highlights of his career. He's going to talk about cognitive science and how it was established, so I won't go into that part of it. I'll focus on some other things. Just so you have an understanding of who Andy is and where he came from, he graduated with Bachelor of Arts and Master of Arts degrees from the University of Alberta, which is in Alberta, in Edmonton. So happens that that's where I graduated from as well, so we know it's an excellent school. In 1966, when he graduated with his MA, he was lucky enough to be selected for a Rhodes Scholarship, which, of course, he went to the University of Oxford in England. He received his Doctor of Philosophy from Oxford in 1973. Now, Canada was very fortunate to get Andy back, however, in 1969 when he became an assistant professor at Carleton. And since he retired in 2014, doing the math, that means he was 45 years a professor at Carleton. And if that's not a record, I'd be surprised. Now, he was very busy for those 45 years. And in fact, in the 10 years since he's retired, he's continued to contribute to scholarship and student supervision, such that his most recent PhD graduate was in 2023. So that's why I'm not sure that retirement is really the right word for what he's currently doing now. Now, Andy has received many awards for his research, and he's been involved in many academic societies, so I'll just hit some highlights. He received the Citation of Merit from the Canadian Psychoanalytic Society. Okay, get that? Psychoanalytic Society. He also had many other roles in that society. He received multiple research achievement awards from Carleton. He has been the president of CUASA, which is the Carleton University Academic Staff Association. So he's got his finger in a lot of different pies. When he retired, he was a Chancellor's professor. And in between 92 and 2004, he was busy being the president and serving other roles at the Canadian Philosophical Association. So again, multiple perspectives. He also took on many other administrative roles, which I won't go into. He's going to talk about his role in CogSci. And he's a productive scholar. He's written 3 books, 6 edited collections, 35 book chapters, 33 refereed journal articles, and many, many presentations in the course of his career. He's also a very dedicated supervisor of students at all levels, undergraduate, master's, and PhD in both philosophy and cognitive science. And in fact, in cognitive science, he has supervised approximately 10 MCOG theses and been involved in over 20 PhD theses. And since cognitive science hasn't been around for all of his 45 years, he's had to cram that in at the end. Now, you just look around for a minute, look around, see all these people here. None of you would be here if it wasn't for Andy, because cognitive science did not exist at Carleton until he created it. It was his vision and dedication that led to us being here today. So now I'm going to have him come up here, Dr. Andrew Brook, and he's going to tell us about CogSci at Carleton and about the research that he's been working on recently. So please. We'll hold questions to the end, okay? But you will get your chance.
Yeah, retirement. That's an interesting topic for academics because we don't quit, we just fade away. And for me, the best part of retirement is I get to do the parts of the job that I still like, and I don't have to do the rest. So I can still supervise students, and Stefan is one of my current students. I get to write, I get to do some traveling, I don't have to do any big classroom teaching. It's a good life. Well, thank you for that, Joanne. I mean, I guess my attitude to doing a lot of things, if you live a long time, you're bound to get a few things done. And, I've been lucky. I've been able to keep going. So I'm not sure what's going to happen in the next hour because I have trouble doing one talk in 1 hour. But Joanne asked me to tack on some stuff about the early history of the program, which I love talking about. We talked about early people, John and Chris and I at lunch. And John and Chris both go back to the very beginnings of the program, as does Joanne. But I also want to talk a little bit about an idea that used to play a big role in philosophical thinking about cognitive science, and that's the idea of a grand unified theory of cognition. I will, at a few points, be a little bit critical. I should tell you that I'm mainly criticizing my former self, because in fact my views on this issue have changed quite a lot in the past few years, and especially in the last few months when I came back to work on it after not doing so for a long time. So that's the agenda, and I'll try to keep it to 55 minutes in total. So the early years of cognitive science at Carleton. Well, let me start by setting the context. And normally I wander when I'm talking, but I can't wander because it's being recorded, so I've got to stay close to the mic. So the context, cognitive science began at Carleton in the early 90s. In the 10 or 15 years before that, cognitive science came into existence. So the name was first used in 77. The journal Cognitive Science began in 77. Behavioral and Brain Sciences began in 78, and the first editor, Stephen Harnad, is still active. He's at UQAM in Montreal, which just got a nice comment on how short the history of the cognitive revolution is. In the mid to late 80s, connectionist systems, aka neural networks nowadays, were first seriously explored, especially in a couple of big collections that came out in 86. MRI imaging got going in the 80s. The first images were taken in 77. Consciousness, which is a subject I care about a lot, reappeared on the cognitive agenda in the mid-80s, 1985. And both graduate and undergraduate research and teaching units were starting. Vassar granted the first degree in cognitive science in 1982. Hampshire College in the US taught the first cognitive science. The world-class UCSD San Diego program, the first cognitive science department in the world, began in 87, and so on. So when I became director of something that still exists, so it has quite a different mandate nowadays, in 91, the Institute of Interdisciplinary Studies, part of my mandate was to plan cognitive science programs at Carleton. And this was something that I was very excited to do because I believed and still believe in the mission of integrated cognitive science. We were able to get this going at Carleton because by a remarkable coincidence, there were people in all four of the core departments. That's psychology, philosophy, linguistics, and computer science that were interested in the enterprise. There are many places in Canada that had a better claim to starting a cognitive science program, but we had just the right mix of resources. And the original planning committee, and I found pictures of 4 of the 6 of them, were Chris Herdman, who's still active, Jean-Pierre Corriveau in computer science, Franz Opacker, whose job was in computer science, but whose PhD was in philosophy, logic from the University of Vienna, Anne Lobstein, and that's the only picture I could find of Anne after a couple of hours of searching. And 2 people, oops, I've got a spelling mistake there, 2 people who just dropped off the face of the earth, Bill Petrusik in psychology, who was a mathematical psychologist. And he doesn't exist on the internet, he doesn't exist in the Carleton archives, he doesn't exist in the psychology department, he has just disappeared. And the other person was Helmut Zobel, the last remaining member of the original committee, who was a linguistic theorist in SLALS, the Studies for Language and Linguistic and Language Studies, School of Linguistic and Language Studies. So that was the original committee. One of the interesting things about Bill Petrusic was, uniquely on this committee, he was a keen advocate of requiring significant mathematical ability in our students, a topic that will return. Of course, if he'd got his way, we wouldn't have had more than a handful of students, but they would have been really good. So we decided to begin with an undergraduate program and a distinguished speaker series, and I'll come back to the speaker series. Dan Dennett gave the inaugural address in autumn 92, and we admitted the first undergraduates, 3, I think, in 93. The first graduate was Asha Sudha, who won the Senate Medal for Interfaculty Studies that year, and who became a member of our department for quite a few years sometime later, and is now at the University of Rochester after some years at the University of Oxford. By now, the committee had added another philosopher, somebody we hired in 93, Rob Stainton, who was actually the first person to have the name cognitive science in his appointment. He was cross-appointed between philosophy and cognitive science, as some of us still are. Plus John, I've already mentioned, and Bill Kelly. In those days, neuroscience was part of psychology. And so even though his appointment was in psychology, he was a neuroscientist. And he was the first neuroscientist to be involved with our program. Rob soon won a Canada Research Chair, and 10 years later moved to Western, thanks to our university's complete unwillingness to try to keep him here, which still irks me to this day. At this point, about 93, what I call, and I think it is remarkable, the saga of our PhD program began. So we just planned a PhD program. We had lots of advice, we had lots of consultants, and put together a pretty decent program. We sent it to the province in 96. It had been approved by all levels at the university by then. The province promptly sat on it for a year. And what this meant was that while we were licensed to offer the program, the province would not give us a penny of support for those students, because what the province had to approve was the funding. Well, with the courage of innocence, we said to hell with it and went ahead and admitted 5 students anyway. I mean, they'd already been approved for admission, they'd been vetted, we were prepared to offer them places, and so we just did. But we didn't have a PhD program to put them in, not one that would generate any funding for the university. So we placed 4 of them in psychology and 1 in computer science. And I mean, that's just, to this day, that boggles my mind. The departments were willing to take them. They got good students, but still. And the students were willing to come, not even knowing whether the program they wanted to enter would be available to them even a year later. One of the 5 stuck it for a year and then didn't come back. Basically, English was not her first language, and she never got her English up to the point where she could survive in the program. The other 4, and there they are, all graduated. And one of the things that's very interesting about them is where they're from. If you notice that 3 of the 4 and 4 of the original 5 were international students from Hungary, Iceland, USA, and France. And the person from France was the person who didn't go on. The reason this is important is in the early years, international students were an important group of students in our graduate program. And the province mucked this up some years after the program started when they introduced incredibly high differential fees for international students without being willing to increase the funding available to international students. So suddenly coming to Canada became much less attractive. So those are the original 4. Zoltan Jakab, who was my student and was the first graduate of the program, won the gold medal that year, which is the top academic medal given at convocation. Jerzy Jarmash, Kamala Johannesdottir, and Ron Boring. And the interesting thing is, not only did all 4 of these graduate, but they're all working in cognition. Something that may not have been true now. They also all became parents. The next cohort, a year later, let me say by a year later, we had our funding approval. I said that's 94 is not right, it should be 97. we'd called the Courageous Four back to our own nest, and we admitted a second cohort of 5, which consisted of Lloyd Balbona, Sam Scott, Diana DeStefano, Sanjay Chandrasekaran, and Vanya Kalajevic. And again, if you'll notice, 4 of the 5 were international students. And I mean, the program in those days was incredibly cosmopolitan. We had students from all over the world. The first 10 students came from 8 different countries. This group also all graduated, all 5 of them, and they're all working in cognition. Lloyd is a senior scientist in a computational psychiatry unit at the University of Saskatchewan. And there's a somewhat sweet story there. When he came to us from the Philippines, he had never seen snow. He had never worn a parka. He'd never worn winter boots. And so the first fall here, about every week he would come to me and he'd say, Andy, that's the end of the snow, isn't it? And where does he end up? In the coldest capital city in Canada. Remarkable. Sam Scott's now at McMaster. Diana is, my information's out of date here. I meant to update it and didn't. That information goes back 20 years at least. She's now a senior policy person with CIHR, the Canadian Institutes for Health Research. Sanjay was the first cognitive science appointment in the history of China, a country of 1 billion people at the time, and they'd never appointed anyone to do cognitive science. And Vanya now is at the Ikerbasque Institute in Spain, which seems to have limitless money. She taught for quite a few years at Memphis before that. And I couldn't find a picture of her. So that's the early history of the department. Let me just round this off with just a couple of last points. 3 of them. In the early years, we deliberately invited as many distinguished speakers as we could find money to get here and as we could persuade to come. So we had Dan Dennett twice, Doug Hofstadter, another typo, Ray Jackendoff, who was Edith's supervisor, Steve Pinker, Zenon Polishin, and others. And part of that was these were names that were known widely in the community, I mean the Carleton community, not just among the narrow band of cognitive researchers, and gave us instant profile at the university level, as well as being really interesting people to listen to. In the early years, we held 3 conferences, and they were all important in their own right. The first was called FICOG, Philosophy and Cognitive Science, which was organized by 2 of the graduate students, Sam Scott and Jerzy Yarmash, and is kind of a predecessor to this conference. The second was a conference on connectionism, and that was the very, very early days of connectionism, which was primarily organized by a colleague at the University of Ottawa at the time, Don Ross. And the third was Cognition in the Brain, which resulted in this collection, which I still think is a good collection, and where the keynote speaker was Pat Churchland from San Diego, who's Canadian. And the third thing I want to note is that we actually received a lot of very important help from cognitive scientists outside of Carleton. And I mentioned some of the more significant people there, Mel Goodale, Mike at Western, Mike Dawson at U of A, who was there in Joanne and Chris's time, Paul Thagart from Waterloo, Martin Davies from Oxford, he's now back in Australia. And I'll even mention just very briefly Don Meeke, who was a very interesting computational scientist at the University of Edinburgh. And I'll mention him because his first job was working for Alan Turing in the Bletchley decoding labs in England. And I mentioned him partly, he was an interesting guy, but also partly because he really illustrates just how short the cognitive revolution has been. 75 years since the very first glimmers, and only 50 years since the name was actually finally codified. Okay, that's the end of the first part of the talk. And I've gone on 20 minutes, so I've got 35 minutes for the rest. So, let me start with the original dream. The dream was of a single integrated cognitive science, uniting the work of cognitive psychologists, computational modelers and AI researchers, linguistic theorists, and others. And exactly how broadly the skirts of cognitive science extend over component disciplines, it varies a lot from program to program, and it can be a matter of controversy. So at least those three core disciplines, all shaped and articulated, of course I would say this, by the brilliant conceptual work of philosophers. Right, Murdo? Now, for many people for a long time, and I'm taking myself as an example of the many people, such integration seemed to require a general theory of cognition, on the model of other big general theories such as Newtonian dynamics, hydrocarbons in biology, or transformational grammar in linguistics. And in fact, the mantra years ago was, who will be cognitive scientists? Science's Chomsky. And Chomsky did it for syntax. Who's going to do it for cognition? So, Polition and Chomsky dreamt the dream, though Chomsky had much more limited hopes than Polition did. People like Jerry Fodor denied that it could ever be done. And interestingly enough, Newell was complaining about fragmentation, about the lack of a single overarching theory, as early as 1972. So before cognitive science even existed as a self-identified discipline, and 51 years ago, I'll come back to what the complaint was, but let me say first a word about what he offered. What he offered as a replacement, and it's too bad Robert West isn't here because I'd love to hear his reactions to this, was a production system called SOAR. And SOAR is interesting. It's interesting for a number of reasons. It's really hard to find out what that anachronism stands for. Acronym, yes. It turns out, and I finally found this last night, that it stands for security, security organization, and artificial regulation. i.e., it was a system commissioned and paid for by U.S. defense funding, and particularly by an agency called DARPA, which played a huge role in cognitive research, especially in the United States, for many years. I mean, every year in Cognitive Science Society, at the annual conference, there would be a DARPA table, there would be DARPA representatives, DARPA would be talking to people about funding their research. And they weren't doing it out of the goodness of their heart. So what he offered as a grand unifying theory of cognition was SOAR. And this took its fullest form in a book that he published in 1990 called Theories of Unified Cognition. Okay, so what was the concern? Well, according to Alan Newell, who I think was one of the most capable of the pioneers of cognitive research, Newell and Simon were, Simon got the Nobel Prize, but I think Alan Newell was every bit as capable. Cognitive science works, or cognitive research works by discovering effects, often by exploring binary alternatives. And I should tell you what the title of his talk was. It was, You Can't Play 20 Questions with Nature and Win. And 20 Questions was a very popular radio show at the time, in which you would try to, by processes of elimination, identify the kind of being that somebody had identified as the target for that program. So the first question would always be, is it animal, vegetable, or mineral? And you get an answer, it's mineral. And then it would be, is it da-da-da-da-da-da? So that's where the title of his talk comes. He listed about 75 of these effects in the talk. By 1990, he estimates there are about 3,000 psychological effects known. And by now, it would be 10 times that many, at least. It'd be at least 30,000, 50,000, who knows? I mean, we've discovered a whole heck of a lot about how particular bits of the mind work in the past 50 years. And today was a good example of that. The talks this morning and the posters were all excellent. I mean, they were all making progress with some issue about how cognition works. So what was his concern? Well, his concern was that while a lot of this work has been very good, what does it add up to? In particular, is any overall picture of the mind emerging from all this effect collecting? And his view was no, that is not happening. In fact, what's happening is increasing fragmentation within cognitive research. Very few people are looking to integrate it. And the subtext of his concern seems to be, though he never says this in so many words, we will not be a science until we have such a general unified theory. And that's the idea I want to look at today. A couple of preliminaries. Who could build such a theory? Where could such a theory come from? What would such a theory look like? And the key question that I will eventually zero in on is, do we need one? Is an overarching theory required for integration? And this, spoiler alert, is where my ideas on the subject have changed a lot in the last while. Well, it should be blindingly obvious, I guess, but I'm going to say it anyway, that there aren't too many cognitive science programs that have a specialization in grand unified theory building. I mean, to make a long story short, nobody trained in cognitive science gets trained to do this kind of theory generation. And if you look at the various specialties in which we do train people, none of them are obvious candidates for graduating people who can do this kind of theory building. I won't say anything more about that, well, except the final point that, I mean, there have been people with this kind of breadth in cognitive science, Noam Chomsky, notably, and also Zen and Plation. And that's a scarce breed nowadays. Next question is, what kind of current work could such a theory grow out of? What could be a precursor to this kind of grand overarching theory? And one might think of a couple of things, and I think there's problems with all of them. One is big multi-year projects that tackle a big problem and try to deal with it exhaustively, such as the interaction of pilots and cockpits, which is one of Chris Herdman's projects. I don't think that's a good candidate for a precursor because these projects tend to be fairly unidisciplinary. I mean, they're big, they're multi-personnel, the problems are very complicated, but the approaches tend to be not extremely interdisciplinary. Well, then what about production systems? This is an idea that seems promising initially, and as I said, Neil offered SOAR. Then there's John Anderson's, not our John Anderson, but John Anderson, 2 generations older. John Anderson's ACT-R, which is what Robert West has worked on in particular. I mean, I don't know if Robert would agree with this, but it's always seemed to me that the differences in microarchitecture, the differences between condition-action rules and production systems and subsymbolic processes in us, seem to be limiting at least the range of kinds of cognition that production systems can model. Plus, there's a bigger question. Alan Newell simply takes for granted that these production systems are not just simulations, they're also theories. And it's not clear to me they are theories. And indeed, I think production systems have at least a partial black box problem in the same way as neural networks do. I mean, they produce the right behavior, as the large language modules do, to a degree that I find absolutely mind-boggling. So, I mean, if anybody asked me, could this happen 10 years ago, I would have said, no, it's impossible. It would be impossible to do that. Purely on statistical regularities, you can get something that behaves so much like us. No, it can't happen. Well, it has happened. But the point is that large language models do not embody or express, and let alone articulate, a theory of what they're doing. They just do it, and do it astonishingly well. So those don't seem to be good candidates. Dan Dennett years ago suggested, as he put it, that we study the whole iguana, that rather than looking at this task or this problem or that effect, we study instead the totality of simpler organisms and build complete theories of simpler organisms. And the problem with that, and nowadays we would say that we also have to do it in normal environments, not in labs, thanks to situated cognition. And the problem with that approach is scaling up. And in particular, how do you scale up from a non-language using organism to us? Well, what about evolutionary theory? I think there's a number of problems there, which let me just very quickly mention two. One is that a lot of the bits of the human cognitive, a lot of the bits of human cognition were selected for very different reasons from what they're used for now. I mean, there was nothing ever selected because it allowed people to design buildings and keep their houses warm. The original skills that allow that were originally selected for because they kept the organisms, lucky enough to have them, alive a little longer, which allowed them to reproduce a little more frequently, which gradually took over the population. This process called excitation is a very important part of human cognition. I mean, what we use our endowments for now is very different from why they were selected for by Mother Nature 250 to 500,000 years ago. And the other thing that's important, an important limitation of evolutionary theory in this regard, is that a lot of what's happened to human cognition happened after the structure was stabilized by evolution. I mean, a lot of human cognitive development is not a process of natural selection. It's something that happens, it's happened since natural selection stabilized us. It happens, warp speed, faster, and with an amazing degree of complexity. So it's not clear where a grand unifying theory would come from. Okay, what about what such a theory might look like? For this talk, I'm going to stick to unified dynamic theory, not structural theory, not architecture. I have, in fact, written about architecture, but I'm not going to talk about it here. So what would a grand unified dynamic theory of cognition look like? Well, for many, Newton's mechanics will be the gold standard to which his theory should aspire. So let's take a very quick look. And from now on, I'm going to be painting with a quite broad brush. I'm just to get a discussion going. Newton's mechanics had three broad parts. Matter, which is viewed as a completely homogeneous and completely undecomposed unit in the universe. So matter is the same no matter where you find it, no matter what it's doing. And Newton, of course, had no idea of the internal structure of molecules and atoms. I mean, he just knew that there was hard stuff out there, and it had interesting properties. Forces, which act on matter and transfer energy, and then laws of motion, how forces affect matter. And there are three laws of motion, which are probably fairly familiar. The best known one is for every action, there's an equal and opposite reaction, which is the principle on which every jet engine works. You blow gas out the back, and it's going to push the engine forward. Okay, the forces acting on bodies in accord with the law of motion, the forces that mattered for Newton were gravity, that masses of matter attract other masses of matter. And gravity in its time was an extraordinarily counterintuitive and controversial notion. And I'll come back to that in a minute. And the other force was friction. To drag one chunk of matter across another chunk of matter takes energy. And later on, electromagnetic force was added, and the strong and weak forces within the atoms and so on, but that doesn't matter. Okay, so the first question is, why posit just this many laws and forces? Well, there's no principled reason. That's all it takes to explain and predict the motion of matter. And Newton's discovery of this was, one of the great scientific breakthroughs of all time. Okay, some of the properties, and this is where the story begins to have implications for grand unifying cognitive theory. Some properties. The first property is that the theory is completely domain general. The laws of motion apply as much to molecules in my brain as they apply to the structure of galaxies. So there's one set of laws for the whole universe. And if we're looking for something similar for cognition, on Newton's model, that's what we'd be looking for. The second thing is, and this is something that Chomsky emphasizes, and I can't go into in any detail, but all the laws are idealizations. Newton never observed any of the phenomena that he expressed in the laws of motion. I mean, in nature, nothing ever goes on at the same speed forever. Everything slows down. There is no reason when you see a bit of gas blowing out of something to expect that something will move in the opposite direction with the same acceleration. So the laws are all idealizations. And similarly for cognition, what's actually going on if there's something grand and unifying going on won't be anything directly observable. I mean, the remarkable thing about science is that, and this is what Newton discovered, that when you put these idealizations together and invent calculus to think about them, you get better explanations and predictions than you get any other way. But there's no reason, up until that point, to think that these extremely counterintuitive idealizations have anything to do with what's going on at all. And that's something else I want you to keep in mind. Next, the components of the theory are counterintuitive. And here gravity is an interesting example. Up until Newton's time, it was one of the parts of conventional wisdom about the universe that causation is always a matter of matter transferring energy to other matter by being beside it, by being contiguous to it. And suddenly here's Newton saying, no, chunks of matter attract no matter how far apart they are. You know, a foot, a mile, or 4 billion light years apart. They attract. And in fact, this idea seems so nutty to Newton's contemporaries that it actually delayed acceptance of his theory for many years. I mean, it's a completely counterintuitive idea. The idea that cause and effect are always contiguous is intuitively very persuasive. And the idea that cause and effect can operate over great distances without any contact between the causing and affecting bodies is very counterintuitive. Just turned out to be true. Okay, and the same thing for the conservation of momentum, but I won't go into that. Another factor is that many of the parts of Newton's theory are very unlike what they explain. Forces, for example. Tell me the last time you've seen a force. You can't. They're invisible. And yet what they explain is the motions of chunks of matter, which are visible. Objects attract, even if they are at opposite sides of the universe. Again, this is not something you can observe. The only way you get to see it is by seeing the dynamics of objects in relationship to one another and figuring out that, damn, there has to be some force tying them together. Otherwise, the whole thing would fly apart. But you can't see that. And the fifth property, and I have to mention this because in memory of Bill Petrusik, dynamics of systems are mathematizable. And as I said, it took the development of calculus to find a way to mathematize the motion of matter. And there's an interesting story here to be told about how knowledge develops, because calculus, it took two of the best minds of the 17th century to invent calculus, Newton and Leibniz. Now we teach calculus to 16-year-olds. Easily, I mean, it's not a problem. The extent to which knowledge gets assimilated and domesticated is a very interesting and complicated story, which I know very little about. Okay, well, other scientists have found similar domain general universal principles. Atomic structure, the valence theory in chemistry, laws of hydrocarbons, dynamics of cell behavior, and of course the neuronal picture of the brain, which is the one closest to us. And again, one where we saw good work this morning. People are doing very interesting work on how neuronal structure and neuronal dynamics correlate with cognitive structures and dynamics. What are the prospects for a similar universal theory of cognition? Well, think of the 5 properties. Laws that apply across all cognition? Not likely. I'll come back to this. An idealization? Well, if there were such a theory, it would be an idealization because it would be a competence theory. It would be the theory of what we can do in the limit. It would not be a performance theory, a theory of how we actually behave. And the difference is that we practically never perform to the level of our competence. There are practically always factors influencing the expression of competence in a way that degrade it, so performance is never at the same level as competence. Parts are counterintuitive. Well, being a competence theory, that would be true. Parts are very unlike what the theory explains. Who knows? But think of the transformational rules in transformation rules in transformational grammar. They, on the face of it at least, are very unlike what they explain. And what about mathematizable? Well, that's a big topic, which I'm sorry to say I am completely incompetent to discuss, and so I'm going to pass over it. So what are the prospects of finding a general idealized theory of this sort? I think they're not very good, and I think this doesn't matter very much. And I'm going to take the last 5 minutes to try to persuade you that there's some merit to both ideas. The chance is not good. The human mind evolved, and we talked a little bit about this a few minutes ago, as various good tricks that allowed organisms to get through threats of survival and reproduction. Slightly higher survival rates, therefore slightly higher reproduction rates, therefore spread. Even with excitations I commented earlier, the chances of all of these good tricks conforming to a single set of principles is, in my view, not high. Second point, the mind is unified under consciousness, which some have contested, but I think is true to a considerable degree. But content, not so much. Representational content is, in fact, not very well unified in the human mind. And disunities break out all over the place. And I say this with full recognition that my hero Kant would be rolling in his grave if you heard me say that. The only existing theory that has anything like properties 1 to 5 is dynamic systems theory. And I think it has its own important limitations. In particular, I think it elides in a lot of important features of cognition. So, in general, I think there's little reason to think that any theory other than dynamic systems theory, any other possible theory of cognition would meet these 5 conditions. Maybe representations or some anti-representational analog of them might be a kind of Newtonian building block. But there are so many different kinds of representations conforming to so many different kinds of operating rules. Think of rules of inference, memory, perception, imagining, feeling, wanting, initiating action. What reasons is there to think that all those representations would be governed by the same rules? I think not a lot. And then think of the different ways in which representations modify representations. Well, sometimes we deliberately choose to modify our representations. Sometimes their semantic content modifies other representations, as in cases of inference. Sometimes the modification process is shaped by system limitations, the famous limitation of short-term memory to 7 plus or minus 2 disconnected bits. I mean, think of it. Nobody would ever design an AI system with that kind of limitation built into it. And so on. Then there's a whole bunch of arguments that such a grand unifying principle can't be built in principle. And in the interest of time, I'm just going to pass that slide over. So if there's no unifying theory, does this matter? Another type of goodie. I see cognition not as a single monolithic kind of thing, changing according to a small set of universal principles, as Newton saw matter. I see cognition as a complex system of widely varying, richly interacting subsystems. Some will operate entirely in the head, some will be in complex interactions with, and even in part extending beyond the head. Each subsystem will have its own operating principles, and yet somehow or other we manage to achieve a fairly high degree of integration in practice, at least in daily life. In some cases, there may even be dynamic singularities that cannot be grouped with other interactions at all. So it just cannot be captured in overarching domain general principles. And both Fodor and, in different ways, Wittgenstein advanced this idea. And then the question arises, of course, if this description is accurate, would this mean that cognitive, quote, science is not true science? And I think the answer to that is very simply no. There's lots of perfectly good science that does not have and does not need grand overarching theories. And some of the work relating how the brain behaves to various cognitive changes that we saw this morning is, I think, a good example of that kind of work. Perfectly good science, no grand overarching theory. Before we stop, let's just go back for a second to what Newell himself recommended. What he recommended to overcome fragmentation. Well, as I said, he recommended SOAR, which he calls a complete processing model and which he viewed as a single unifying theory. And I commented on this earlier, I won't say anything more about it. But his other three recommendations actually have very little to do with grand unifying theories. I mean, what he recommends is to begin to end the fragmentation of cognitive science, we should put all the experimental work on a topic together. We should analyze individual complex tasks completely, as, for example, children's mathematical abilities. We should search for mechanisms and procedures that are common to many tasks. Okay, we can accept all those recommendations without for a second dreaming that there could be a grand unifying theory of cognitive science. Does this mean that fragmentation is not a problem? No. It is, if anything, in my view, even more a problem than it was 50 years ago when Newell wrote his famous article. It's just that the way to overcome the problem is not by seeking a grand unifying theory, he said to his earlier self. There will never be such a theory. Thank you. And remember to speak into the microphone because the whole thing's being recorded.
Okay, so I see Raj in the back, and then I'll go to Jim next. So.
Thank you, Andy, for continuing to teach us. My question is about the time scale of development. So you mentioned several times that how cognitive science is a very young discipline, sort of in its infancy, right? And when you talk about Newell and Chomsky and their innovations, the mathematization that was required for them came just a couple decades before with Turing's work on computing general theories of algorithms. So it wasn't long after a mathematical framework was there that a bunch of grand leaps in cognitive science were made. But the study of a sort of a mechanical theory of the mind is just mid-20th century. That's the only time it was actually possible. Whereas with the study of the Newton and calculus, that work had been going on for centuries. So could it just be that we're just so in our infancy that just that is why it's so hard to even fathom what a unified theory might look like? Like maybe it's like, what the world might have looked like centuries prior to Newton and Leibniz and the rest of them.
I mean, that's a concern that I think really has no answer. And I'll give you another example of it because I think it is a very real concern for any activity as young as ours. There is a view of consciousness around, which is shared by Chomsky and some other people like Colin McGinn, that consciousness is as close to us rationally as physics is to dogs. I mean, there's something out there to be studied, but we just don't have the horsepower to study it. And Dan Dennis' response to that, which in general, I have a lot of sympathy to is, you're way premature to say that. Come back in 100 years and see where we're at. And I think, what I'm doing is painting a picture and assessing probabilities. I think it's highly unlikely that there will ever be a Chomsky or a Newton of cognition. But I also recognize that I could be dead wrong. And if I am dead wrong, it'll be for patterns that I can't see, that I don't know about, that I can't observe. So I think it's a real concern, and I think the only response is, looking at all the considerations, what's likely.
Thanks, Andy. I'm interested in the role of simplicity of what we perceive to be grand unified theories, because physics gets to enjoy dealing with great theories that can fit on one page. I've been thinking about things like how bodies work and how we've been building up an understanding of the relationship of kidneys and lungs and the heart, and we have this basic understanding of what all the organs are, what they're for, and even how they interact. And we don't call it a unified theory, perhaps because it is complex. We've got evolution, which is its own sort of unifying theory in one domain, but then the central dogma and cell differentiation. But we don't have anything like that for the mind yet. But I was wondering if perhaps what we have for maybe the biology of bodies and organs is the kind of unified theory we might hope for. And if there's a role in general of like simplicity. I mean, even Newton has multiple forces, not one force to explain everything. There are multiple forces. So is it, is a unified theory a subjective thing, perhaps according to some level of simplicity?
Yeah, I mean, I don't want to get into example mongering, but in this case, I think throwing up a counterexample or two might be interesting. As Jerry Fodor famously said, what would a science of Tuesdays look like? And yet we can talk quite rationally about days of the week. We just can't do science over them. Some people, as I say, what would a science of cognition look like? Well, we have no idea any more than Fido has any idea what Newtonian physics might look like, but there could be one. And there's just a whole host of different cases. I mean, what ties living tissue together is the science of hydrocarbons and how they create muscles and membranes and fluids like blood and blah, 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 blah. And there could be such a thing for cognition. It seems to me extremely unlikely, but there could be. And as I said, whether or not there can be, that doesn't stop the activity of integration. And I wish we did a great deal more of it.
I guess what I'm wondering is, if we assume that we can't reach some sort of grand unified theory, how much do we rely upon the other unified theories that are out there, such as evolution, or if we look at computation, there's a set of rules that computation typically follows, axioms for math. There's all these different things that we are relying on, and if we are abstracting off of them, do we just say we have unified theories, things that connect everything together, as opposed to one? How do we look at this?
Well, I mean, I'm shameless. I'm willing to steal anything that would be useful. One of the big questions that underlies how much we can import from other kinds of more theory-structured intellectual activities is the old question of how much the mind or cognition can be mapped onto the brain. And you have people like Polishin and Dennett arguing that it can't be. That the only way to understand cognition is in the proprietary language of cognition, language of beliefs and desires and representations and so on. And if you ever try to reduce away from this, you will end up with descriptions that don't capture significant regularities. If, on the other hand, the mind can be, as my philosophy of science friends would say, smoothly reduced to the brain, or as the Churchlands would say, eliminated in favor of a story about the brain, then the prospects for boring from other more scientifically structured activities are much higher. There's a nice, on the one hand, on the other hand answer for you.
So Rob's not here, so I can try to imitate what he might say. It's speculative necessarily. So Rob has actually, in his more recent work, been trying to explore combining ACTAR with generative networks. So I think he's also feeling that he's running up against the wall of what you can do with a production system, and that these new networks are clearly much more capable of in more complex behaviors. I guess I have a question, pertaining that. What constitutes a theory or a cognitive theory? Like if you look at, say, these large neural networks that are, say, the large neural network that powers ChatGPT, that is a translation of essentially natural language into formal language, which in many ways we would say that was our objective potentially in characterizing how language works, was a translation of language into formal language. So to what extent is it like not a theory because just because of the interpretability issue? What are the criteria for something to be a theory?
I'm inclined to say something particularly lame, such as if I had a good answer to that question, I'd publish it. I think the boundaries of the cognitive are essentially contested. And depending on other commitments you have and depending on your interests and so on, different people can legitimately draw them in different places. And so for there to be any chance of you and I agreeing on where to draw them, we'd have to start looking at examples and look at contexts and look at tasks. And I mean, part of what complicates this is that whatever you decide to include within the cognitive, it's bound to be in incredibly complex and dense interactions with the non-cognitive. I don't know, does that help?
Yeah.
Okay. Hold on. There you go.
So I'm going to take up your suggestion that we give up on this idea of a unified theory and pick up on the second last bullet point about the problem that fragmentation would still pose. And I'm looking at all the displays out there. I find it striking that there's this conversation that goes on between neuroscience and computer science. And that suggests to me that even if you don't want to be a reductionist a la Churchland or something like that, you're still stuck with this need to work out a way in which there's this kind of inter-theoretical understanding happening. And is that a fair problem to characterize as a remaining problem if you get rid of it? And if so, what thoughts do you have about it?
Yeah, I'm not locking into the concern, Peter, partly because I was trying to get the slides back up. Can you say just a bit more about where you want to go with that?
When we talk about fragmentation remaining and it still being a problem, what exactly are we talking about? And one way to characterize that would be to talk about all the different activities that are engaged in the practice of the large umbrella of cognitive science. And two of them would be neuroscience and computer science. And a number of the displays point to that. You'll see MRI imaging of the brain as a way of trying to measure something that is being tested partly through an implementation of a particular kind of computer science model, whether it's ChatGPT or image recognition or something like that. So these sciences are still very active and in some sense still need to talk to each other and for us to understand exactly what it is we're doing and what we're observing. So even if there's no unified theory, we have to be able to one phrase would have been once upon a time into theoretic reduction and stuff like that, but I'm not a big fan of reductionism So kick that out, we're still left with something I would call intertheoretic understanding.
Well, I mean, a slogan is integration without unified theory. And there's all kinds of ways in which the kind of results that we saw in the posters, the kind of results we saw in the talks this morning, can be connected to other results. And doing so is almost inevitably bound to be informative and interesting. And you can do that kind of connecting, that kind of integrating, without having an overarching theory of what's going on. You can do it just by taking particular results, you can take other particular results. And I think that we need a lot more of that. I mean, eventually we need to build up pictures of how the subsystems work and then how the subsystems interact to produce the kind of activity that we see from intact adult human minds. And the more of that we do, the better. And my suggestion is that we don't need a grand unifying theory to do that kind of integrating work. And so we shouldn't wait to get started until we find one, because we're probably never going to find one.
Thank you. Okay, Andy, thank you very much for your presentation. You can clap again. I want to mention a couple of things. One is that many of you are familiar with the lovely new boardroom that we've created on the 22nd floor, and we're going to name that the Brook boardroom after Andy. And finally, I want to thank the people who put this conference together. First among them is Tycho Brook. There are multiple other people who have helped out. Can I get you to stand up if you're on the organizing committee, please? Okay, organizing committee. Yeah, come and take a picture. Yes, excellent idea. Come on, organizing committee. But Andy, why don't you stay up there and somebody take a picture? Okay, why don't we do that?
Can you take a picture?
Yes, Corey.
Of all of us. Thank you.
These kinds of events don't just happen, they have to be organized and arranged. And I think we've had an amazing set of graduate and undergraduate students who have come together and organized. What? Oh. Okay, I don't think I really need to come up here, but there we go.
Come on, Car, you got this. Okay. Commitment.
You're blocking James. All right. All right, thanks everyone, and see you next year.